Hello everyone, I am C. Nitya working as Assistant Professor in EC Department, R.M.K College of Engineering and Technology. And welcome to the session. I am handling the subject called Basics of Biomedical Instrumentation. The subject code is OMD 551. Today we are going to see about microelectrodes. As we already see what is electrode in the previous sessions, again we will have a short recap on it. Electrodes are a device that converts ionic potential into electronic potential. So the acquired signals like ECG and EEG and EMG, that is electrocardiography, electroencephalography, electromyography. The electrode potential is developed across the interface proportional to the exchange of ions between the metal and the electrolyte of the body. Consider the figure that has two electrodes is kept on the chest of the patient, so that we are going to measure the electrode potential between these two electrodes. So our body mainly consists of electrolytic solution, that is our body is first of all filled with a fluid that will act as an electrolyte. So depends based on that electrolytic solution and the interference of this electrode will generate the signals. So this signal will be displayed in the display unit. Now we are going to see the types of electrodes. Based on the anatomical location, we can use different types of electrodes for measuring bioelectric signals. We will see the types of electrodes. First one is surface electrode, microelectrodes, and depth and needle electrodes. Today we are going to discuss about microelectrodes. Microelectrodes are normally used to measure the bioelectric potential near or within the signal. So we can also call it as an intercellular. While measuring the potential of the microelectrode, whereas this microelectrode is located within the cell and the reference electrode is placed outside the cell. So its diameter is very small, so it will not create or any damage to the cell while we are inserting. Size of the cell is of about 50 microns. The diameter of the tip of the microelectrode is ranging from 0.5 to 5 microns. Now we will see the type of microelectrodes. Microelectrodes can be classified into two types. One is a metal microelectrode, or we can call it as an metallic electrodes. Then second type is micropipette or non-metallic microelectrodes. First we will see metal microelectrodes. Metal microelectrodes is a fine needle of a strong metal that is insulated with an appropriated insulator up to its tips. Metal microelectrodes are formed by electrolytical etching the tip of a fine tungsten or an stainless steel wire to a fine point. This technique we can call it as an electropointing. This etched metal wire is supported by a large metallic shaft. This metallic shaft will act as a steady mechanical support for the microelectrode while we are using for measuring. Then second point is means of connecting microelectrode to its lead wire. The microelectrode and its supporting shaft are usually insulated by the film of some polymeric material of varnish. Only the extreme tip of the microelectrode will remain uninsulated. Two different materials are used to make a supported metal microelectrode. That is, strong insulating material is used for giving support, that is basic support, and a metal with a good electric conductivity used at the contacting portion of the electrode. The measurement of the bioelectric potential requires two electrodes. The voltage measure is the difference between the potential of the microelectrode as well as the reference electrode, and it is the sum of the three potentials. Impedance of the microelectrode tip is inversely proportional to the area of the tip and the frequency. When the electrode output is coupled with an amplifier, the low frequency component of the bioelectric potential will be attenuated if the high impedance is not required. We know that attenuation is used to attenuate the high input impedance to give the low input impedance. So this equivalent circuit represents the metal microelectrode. The metal is coated with an insulating material so that there is a capacitance set up between the metal and the extracellular fluid. This is called as a distributed capacitance, CD. Consider the microelectrode to be a coaxial cylindrical capacitor. We will see the descriptions that is involved here. EA and EB are two electrodes with an electrolyte potential. A is a metal electrode and EB is a reference electrode. So these are all the descriptions of the equivalent circuit of metal microelectrode. Next we will see about non-metallic microelectrode or micropipette. Micropipette electrode is prepared by first filling a glass tube with the metal that has a melting point near the softening point of the glass. Here the glass is not only providing a mechanical support but also serves as the insulation. The active tip is the metallic area metals such as silver solder alloy and platinum, and then silver alloys are used. The section of the fine bore glass capillary will be heated with the burner to softening the point. It is then rapidly stretched to produce the contraction. Special devices known as microelectrode pullers that heat and stretch the glass capillary in an uniform way to fabricate micropipettes. The two halves of the stretched capillary structure are broken apart of the contraction to produce a pipette structure that has a point diameter of order of 1 micrometer. It is then filled with an electrolyte solution, that is frequently 3M-KCl. A cap contains metal electrode is then sealed to the pipette. The metal electrode contains the electrolyte within the pipette. The electrode is frequently a silver wire prepared with an electrolytic AgCl surface. Platinum or stainless steel also used occasionally here. Now we will see the equivalent circuit of the non-metallic microelectrodes or micropipette. The internal electrode in the micropipette give the metal electrolyte interface components, that is R.M.A, C.M.A and E.M.A. There are two potential associated with the tip of the micropipette microelectrode. The liquid junction potential EI corresponds to the liquid junction set up between the electrolyte in the micropipette and the intracellular fluid. In addition, a potential known as a tip potential ET arises because the thin glass wall surrounding the tip region of the micropipette, which behave like a glass membrane and has an associated membrane potential. All the associated DC potential are lumped together in the source EM, which is given by the equation EM is equal to EJ plus ET plus EMA minus EMB. So this shows the description of the equivalent circuit of the micropipette electrode. So hope you all enjoyed the session. Thank you.